Greetings! Welcome to Electronics2. This is lecture number 19 and I am Razavi. Today we will spend some time continuing our discussion of frequency response and in particular go over what we call the Miller's theorem or the Miller effect, an important and interesting phenomenon that happens in circuits, especially at high frequencies. And the theorem that Miller proposed also helps us with circuit analysis. And then we will also look at the high frequency model of bipolar transistors to see how we analyze circuits that have bipolar devices in them. And of course, in the next lecture, we will talk about high frequency model of MOS transistors. All right, but before we go there, let's just briefly review what we covered last time. We talked about the Bode's rules, and we saw that Bode says when we are plotting the magnitude response of a function, of a transfer function, as a function of omega, the slope decreases as we pass a pole frequency. So for example, from here, we go here, and the slope decreases by 20 dB per decade. So this becomes minus 20 dB per decade. And then if we are passing a zero, like in this example, then the slope increases by 20 dB per decade. So we go back to a slope of 0. So that's a very helpful rule to remember for sketching the frequency response of circuits. And then we also talked about finding the poles of a system by inspection rather than by trying to draw out the entire small signal model and writing KVLs and KCLs. And our thought process was like this. If at a given node, I can find the resistance to AC ground and the capacitance to AC ground, then the product of these two, inverse of that, will give me the pole. So the pole associated with this node will be 1 divided by Rg times Cg. That would be omega. If you want to find F in hertz, you would have to divide that by 2 pi also. Similarly, at this node, I have a resistance to AC ground and the capacitance to AC ground. So I can say that the pole at this node is given by 1 divided by Rd times Cl. So that's great. It very quickly allows us to write the transfer function of a circuit like this, as we did last time. And then we can quickly plot the magnitude response as well, because we have the pole frequencies and we can use Bode's rules. However, we also noted that there was a complication, and the complication arises if the circuit contains a capacitor, for example, between two nodes, neither of which is ground. So you might call this a floating capacitor, right? It's not grounded on one side. It goes to one point in the signal path and another point in the signal path. So how do we deal with this, right? That's the complication. And that's where Miller's theorem comes into the picture. So we're going to talk about Miller's theorem first and then see how that leads to the Miller effect, which is something that happens in our circuits. So let's talk about Miller's theorem and see what he says. So Miller's theorem comes to help us in this situation. Miller's theorem says that we can decompose this floating capacitor to two grounded capacitors. Okay? So then suddenly the circuit becomes manageable. So let's take it step by step and see how this works. All right, so Miller says here, suppose we have some general circuit and we have two nodes in the circuit. So here's a node, we call it P. Here's another node, we call it Q. And there are lots of wires and stuff connected to these nodes, various types of components. And we are focusing on one impedance that goes between these two. Okay? And this impedance we will just call ZPQ, an impedance connected between P and Q. All right? So we know ZPQ. Okay, that's the value we know. For example, we know the value of this capacitor. All right, now we also know the voltage from node P to ground. So let's say there's a common ground here, and we call this voltage VP. And we also know this voltage VQ. Okay, that makes sense, right? In the circuit, I should be able to find this voltage in AC, in small signal analysis with respect to ground, and that voltage, right? Okay, so now Miller says that it is possible to transform the circuit to a different circuit. And in this new circuit, what we have is still we have all of the devices in here connected to P and Q. Everything is the same. So we have P, and then we have Q. These are two nodes. And the voltages at P and Q have not changed. So this is still VP here, and this is still VQ with respect to ground. This is our common ground. Now, we remove this floating impedance, which is connected between P and Q, and we replace it by two grounded impedances. One connected from here to ground, and one connected from here to ground. Okay, this is all ground. And we'll call this ZP. We'll call this ZQ. So we would like to see under what conditions these two circuits will be the same, right? If they are the same, if the voltages and the currents in this circuit are the same as those in this circuit, then of course the circuit doesn't know that we replaced this impedance with these two grounded impedances. Okay, so we're going to show under what conditions that happens. In other words, what we don't know right now are ZP and ZQ. We already know ZPQ and VP and VQ, and we know that VP and VQ have not changed because the circuit is equivalent, but what we don't know are ZP and ZQ, so we have to calculate those. Okay, but you can immediately see the beauty of this result, right? Because if I have a floating capacitor from here to here, like this, I can convert it to two grounded capacitors. And those grounded capacitors would be similar to these, right? So this will be gone, and we have two capacitors on these sides, so we can go back to finding poles by inspection. So that's the nice result that comes out of this theorem. Okay, so let's try to find ZP and ZQ from here. I will try to do this. I say that how much current is this impedance drawing out of node P? Okay, so current drawn from P. Well, it's simple, right? You have VP minus VQ divided by the impedance, right? That's the definition of impedance. Voltage divided by current, or current is equal to voltage divided by impedance. So I can say that it's given by VPQ VP minus VQ. So we have VP minus VQ, the voltage difference divided by the impedance divided by ZPQ. Okay, so that is the current that this branch is drawing from node P. Now, what do we expect to happen in this circuit? Well, this branch should draw the same current, so that this part of the circuit does not feel the difference between these two. So the current through this branch has to be the same as what we calculated over there. How much is this current? Well, one side is 0, one side is VP. So it's VP over ZP. So we have another equation, and that's VP over ZP. This is the current from node P in this circuit. This is the current from node P in that circuit. And these two currents have to be equal. Okay, so let's equate them, right? And what we need to do is now find for ZP, because that's the unknown quantity. So I will go back to black and I will write ZP. You can see that I can bring this to the other side and I divide these. So what I get is ZPQ divided by 1 minus VQ divided by VP. That's the amount of impedance that we have connected from node P to 0, which we call ZP. So if we choose that impedance like this, then the current that flows this way is the same as the current that flows this way. So these parts of the circuit don't feel that we have made a change. All right, the same thing has to hold for node Q. So there's some current, let's say, going this way from node Q, right? Which we can calculate would be VQ minus VP over ZPQ. And there's some current going this way, which would be VQ over ZQ, because this side is grounded. So we do the same thing, and the result will be this. So ZQ will be ZPQ divided by 1 minus VP over VQ. Okay, so very simple. Because we already know VP, VQ, and ZPQ, we can find the new impedances, these grounded impedances. And once we are there, the circuit has been reduced from this case, which was more complicated to analysis, to this case, which is hopefully simpler to analyze. All right, so this is what we call Miller's theorem. Miller says that a floating impedance can be decomposed into two grounded impedances that are obtained by these equations. Okay, that's great. So let's go over some examples just to get comfortable with all of this so that we know how nicely this Miller's theorem helps us. So here's an example. I go and buy an amplifier, okay? So I buy an amplifier, and the amplifier has some voltage gain. So let's say the voltage gain is minus 10. So it's an inverting amplifier. All right? Okay. And I connect a resistor between the input and output. Now, why exactly I do that is not clear at this point. We will see sometime later that this is actually an interesting feedback technique. But for now, don't worry about it, right? You just have a resistor. And we call this resistor RF. So this is a floating resistor, right? Because it connects from one point in the signal path to the other point. We would like to convert this to two grounded resistors. Okay? So how does it work? Well, very simple. So ZP, so we will say that this is equivalent to, so again, let's call this P and Q. So what we have is this. Now we have a grounded resistor at the input, another grounded resistor at the output. We call this P and Q, so let's call this RP. And let's call this RQ. Okay, how much is RP? RP is given by the original resistance, right? So RP, I'm rewriting this equation, is given by the original floating resistance, the ZPQ, which is now RF, divided by 1 minus, this is VQ over VP. VQ over VP is this voltage divided by this voltage. Is this voltage divided by this voltage. What do we call the output voltage divided by the input voltage? For small signal analysis, we call it the voltage gain. So that's this, right? So that's 1 minus AV, and that comes out to be RF over 11. Okay, so that is this resistor that now appears from the input to AC ground. How about this resistor, RQ? RQ is given by RF against VPQ divided by 1 minus. Now this time what we have is VP over VQ. VP over VQ. But we're going to write that as 1 over VQ over VP. Why? Because VQ over VP is actually a meaningful quantity, is the voltage gain, right? What we really have is that this is the cause, this is the effect, right? If this moves, this moves. But we can't say that if this changes, right? In a simple amplifier, that may never happen. If you build an amplifier like this, and then you connect something to the output and start changing it, the input doesn't change, right? At low frequencies. So it's meaningful to say that the VP over VQ is actually 1 over VQ over VP. And this VQ over VP, of course, is the voltage gain, right? So we say RF 1 minus 1 over AV, and that would be RF divided by 1 minus 1 over 10, so 1 plus 1 over 10, right? So that's RF over 1.1. Okay, so let's digest this result. It's interesting. It says that when I connect a resistor from the input to the output of an amplifier, and the amplifier has a negative gain, it's a non-inverting amplifier, right? The result is equivalent to having a resistor from the input to ground, which is actually quite lower than the original resistor. The original resistor was RF, let's say 1 kilo ohm. The new resistor, the grounded resistor, is RF over 11. So, in other words, the input resistance of the circuit is this much, even though the original resistor that we connected between the input and output was higher. So this is one aspect of what we call Miller effect. So the Miller effect says that the impedance ZPQ is divided by 1 minus AV as it appears at the input. Okay, so we say as it appears, right? As it appears, meaning as it becomes a grounded impedance. So let's say that I bought this amplifier originally, it was a common source amplifier and its input impedance was infinity, right? Okay, but now that I connect this resistor from the output to the input resistance is equal to RF divided by the voltage gain, by 1 plus 1 minus the low voltage gain. The voltage gain is negative, so RF over 11. So the input resistance is quite lower than even the feedback resistor. Now, whether that's a good thing or a bad thing depends on the application. In some cases, we would like to have a low input impedance. In some cases, we don't. But if we do, this is an interesting method of reducing the input impedance of a circuit. Okay, so when we say Miller effect, at least in the context of what we have studied so far, it just means that there was an impedance between, let's say, the input and output of an amplifier, and this impedance got divided by 1 minus AV when it was decomposed, and one part of it became the input impedance of the circuit. All right. Okay, so there's a quiz that I want to give you. I'll just write it here, and I'll give you 1 minute to think about it. What if we buy an amplifier, and the amplifier has a gain of 10, but plus 10? Okay, then what happens? So think about it for 1 minute. Okay, so what did you conclude? Well, so we've got to go back here to these numbers and see exactly what happens. So let me change the color of my pen. So what we see is that AV is now plus 10. So 1 minus 10 is minus 9. So what we have is RP is equal to RF divided by minus 9, right? Instead of RF over 11. So we have created a resistance at the input that is negative. Is that surprising? It is sort of surprising. Is that useful? Sometimes it is useful. Can we do it? Yes, we can. So there are some circuits that actually benefit from this property. We can create a negative resistance by techniques such as this technique. Okay? So, but we won't talk about them here. All right, let's go to another example and make things a little more interesting by changing the feedback component to a capacitor. After all, we are interested in the capacitors in our circuits because, as I said last time, capacitors are sort of the enemy of high frequency operation. So again, I buy this amplifier. It has a gain of minus 10, and I connect a capacitor between the input and output. I will call that CF. Now, why do I do that? We don't know at this point why we are connecting a capacitor between the input and output. Is it a good idea? Is it a bad idea? These things will be studied later. But for now, let's just say we did that. And I'm going to apply Miller's theorem to this capacitor. So Miller says, all right, well, we're going to have, here's our amplifier, the original amplifier. And here's our original amplifier. So we'll take this impedance and convert it to two grounded impedances. We call this node P, this is node Q, this is P, this is Q. Okay, so how much is this impedance here? Remember, it said take the original impedance and divide it by 1 minus AV. So what's the impedance of a capacitor? The impedance of a capacitor is 1 over CFS. So we have to take this impedance and divide it by 1 minus AV. So we have to divide that impedance. So we divide that impedance 1 over CFS by 1 minus AV. So 1 minus AV. Okay, that's on this side. All right, how about at the output? At the output, we do the same thing based on that equation. So we said we take the original impedance, CFS, and divide it by 1 minus 1 over AV. So 1 over AV. That's this impedance. Okay, so now what we are curious about is what is this exactly after we did all of this? Is it still a capacitor or is it something else? What is it? Okay, well, let's examine this very carefully. We have 1 over something, just like the original capacitor was 1 over something. In the denominator, we had an S for a capacitor. In the denominator, we have an S for a capacitor. In the denominator, we had the value of the capacitor multiplied by S. In the denominator, we have something multiplied by S. So we can call that the equivalent capacitor, right? So we see that the equivalent capacitor is CF times 1 minus AV. Okay? So if AV itself is minus 10, this will be 11 times CF. So it will be a larger capacitor as far as this input impedance connected to ground is concerned. How about here? Same story. 1 divided by S, so all of that remains would be the equivalent capacitor. So this would be equivalent to CF times 1 minus 1 over AV. AV is minus 10. This is 1 plus 1 over 10. So it's about 1.1 CF, right? 1.1 CF. On the other hand, this was 11 CF if AV is minus 10. Okay, so let's summarize what happened here. We bought an amplifier with a gain of minus 10. So AV minus 10. We had a capacitor connected between the input and output, P and Q. And then after we applied Miller's theorem, we got this. We got a capacitor to ground, which is 1 minus AV times CF. And we got a capacitor from here to ground, which is 1 minus 1 over AV times CF. So this is also what we call Miller effect. So this in particular is called the Miller effect. And what this means, and this is what was observed by Miller himself, is that because we had a capacitor connected between the input and of an amplifier, and the gain was negative, the resulting equivalent capacitance seen between the input and ground is quite larger. It's the original capacitance, that one, multiplied by, for example, 11 in this case. Right? And that's what Miller observed. And he said that because you have a capacitor between the input and output, this overall circuit becomes slower. Why? Well, this is coming from something. Where does it come from? Maybe it's coming from another amplifier. So let's draw another amplifier here. And this amplifier says, how much capacitance do I see? How much capacitance do I have to drive? And we say, well, this is the capacitance you have to drive, right, equivalently. So that amplifier has to drive all of this capacitance. So this amplifier will suffer from a high load capacitance because this feedback capacitor is now multiplied by 1 minus AV, and AV is a negative number. All right? So this becomes a major issue in many high-frequency circuits, because in many circuits we do end up with a capacitor between the input and output of an inverting amplifier. We don't want it, but we inevitably have it. So now we have to deal with Miller effect. In fact, there's a term for this. We say Miller multiplication factor. we say that this capacitor has experienced Miller multiplication because it is multiplied by this number that is quite larger than 1. So we have to deal with this Miller multiplication effect when we have capacitors between the input and output of inverting amplifiers. All right, so that's very important. So we see that Miller's theorem gave us two types of tools in our analysis. One is, how do you go about converting a floating capacitor to two grounded capacitors? So that's great, right? Because now we can try to find the poles by inspection. Also, the second important result is that Miller tells us if you have a capacitor between the input and output of an inverting amplifier, it's bad because the input capacitance will be quite larger, right? It gets Miller multiplied. It experiences Miller multiplication. So we don't want to have a capacitor between the input and output of an inverting amplifier. All right. Now, again, the question we can ask is, what if AV is positive, for example, plus 10, then this capacitor will come out to be 1 minus 10, so it'll be a negative capacitor. And is that a good thing, bad thing? Does it happen? Yes, it does happen. And sometimes it's a good thing. Sometimes we actually utilize that effect in high-frequency circuits. We use a negative capacitance by means of this technique. Very well. Let's move on and look at another example. So here's another example. Suppose I have a common source amplifier. Very simple. Here's a common source amplifier. V in, V out. We can call these also nodes P and Q. And I connect a capacitor between these two. We call this CF. Why do I do this? At this point, we don't know. But let's just say there's a capacitor there. Okay, so can I apply Miller's theorem to this capacitor? Sure. So Miller says that you can decompose this capacitor to one here and one here. The capacitor at node P is given by the original capacitor, CF, multiplied by 1 minus AV, the voltage gain. How much is the voltage gain from P to Q? Well, so we know VQ over VP equals minus GMRD, right? That's the voltage gain of the circuit, voltage gain of a common source stage. So this capacitor will be Miller multiplied, so it has to multiply by 1 minus AV. So this capacitor at the input is now given by CF times 1 plus GMRD. So the input capacitance is larger, right? It's not just CF, it's CF times 1 plus GMRD. How about this capacitor? This capacitor at the output is now CF times 1 plus 1 over GMRD. So it's a little larger than CF. This is not a very large number, as we saw, like 1.1, right? But it's a little larger than CF. Okay, so it's very simple, right? We took the troublesome situation, which I mentioned at the beginning of this lecture, namely a capacitor connected like that, and we decomposed it into two grounded capacitors. So now we can associate poles to these nodes, find the poles by inspection. And it's pretty simple, right? Okay. However, I need to give you a caution here. We won't go through the details of this caution, but you should know this. So, 1. This circuit has only one pole because it has only one capacitor. This circuit has two poles. So, Miller's approximation has introduced a new pole. Now, why did I call this approximation? What approximation did we make? Did we make an approximation so far? Well, yes. Right here, I made an approximation, but I didn't tell you. I said that the gain, the VQ over VP, is minus GMRD. That's true at low frequencies when this capacitor is not here. But when the capacitor is there, we can't say that this voltage gain is the same. This capacitor does something. It has some impedance. It draws some currents. We can't say that the voltage gain is just minus GMRD. So that's the approximation that we are using with Miller's theorem. We are using the low frequency gain minus GMRD to mean AV, this AV. In reality, AV should be the gain at the frequency of interest, not at low frequencies. Okay? But this approximation has these consequences. Now, most of the time it's okay. It doesn't really bother us that we have these issues. But of course, in some cases, we do have to be careful. Okay, the second point that comes out of this is that the original circuit has a 0 because of the CF. We will see that much later. But here, we don't have a 0. So Miller's approximation has eliminated the 0. Okay, so again, I'm not delving into these that much right now. This is just so that you have in the back of your mind, you know that we are making an approximation and there are some consequences, but they're usually not very serious in actual circuits. Very well, let's move on and talk about the high frequency model of bipolar transistors. Okay, so we saw that generally we don't like capacitors because capacitors give us poles and poles reduce the bandwidth of any circuit, right? So obviously we need to identify all of the capacitors that we encounter in a circuit and then see how we should deal with them. And the most common type of capacitances arise from the components themselves, in particular from the transistors. So I need to identify, when I see a bipolar transistor, what type of capacitances it introduces into the circuit. So that's why we're going to look at the high frequency model of bipolar transistors. We have seen the small signal model of bipolar transistors in Electronics 1. So we need to go add some capacitances to it to make it a more complete model for high frequency analysis. So what are those capacitances? Okay, well, it's not that hard. Here's our simple structure that we've seen in Electronics 1. We have the emitter terminal here, the base terminal here, and the collector terminal here, right? And for example, in an NPN transistor, usually we have N here, P here, and N plus here. So here we have a PN junction. And remember, the PN junction has a capacitance associated with it because there's a depletion region. So there's a depletion region here. And that gives us a junction capacitance. We'll call it CJE. Junction capacitance associated with the base emitter junction. There's another junction capacitance here between the collector and the base. So there's a depletion region here. And that also gives us another capacitance, which we call CJC. The junction capacitance associated with the collector. Okay. All right. So it seems that we have only two capacitances for the device, right? But it's a little more complicated. So let's change the color and see what happens. All right, so for that I need to draw the transistor horizontally this way so that we remember what was happening from electronics 1. When the bipolar transistor is operating in the forward active region, so here's the base, here's the emitter, and here's the collector, right? So remember what happens? The electrons start from the emitter, pass through the base, and enter the collector. And the important point was that the movement of the electrons inside the base area is by diffusion. Diffusion is like you drop some ink into a glass of water and the ink just diffuses away. So for that diffusion to occur, we need a change in the concentration of electrons. We need a gradient of concentration of electrons. So in the base region, if you remember, we have a gradient, meaning that here, this is the density of electrons, density of charge carriers, electrons, as a function of x. So we need to have a profile here, we need to have a slope, so that when an electron enters from the emitter to the base, it just rolls down the slope and gets to the collector. So we have stored some electrons here at any moment in time, right? There are lots of electrons sitting here. So we have, to turn on the bipolar device, we have stored, we delivered some electrons to the base region. And that's different from the depletion regions that we have here and here, right? That's completely different. So anytime I can store charge into something, that something can be modeled by a capacitor. So we have to include that as well in our model. So here comes the overall model. We start with the low frequency model that we developed in Electronics 1. If you want to include channel the early effect, that's okay, we use that. So this is GM V pi, this is R pi, and the voltage across this is V pi. All right, so we have the base, the emitter, and the collectors. So let's drop in all the capacitors that we have identified so far. There's a capacitance between base and emitter, this junction capacitance. So we're going to add that in here, call it CJE. There's a capacitance between the base and the collector, which we call CJC. So we'll add that here, we call it CJC. And finally, there's an equivalent capacitance associated with this charge that we deliver to the base. We want to turn on the device, we have to deliver that charge to the base. We want to turn it off, we have to take that charge away. So it's just like a capacitor. So we'll just call that something. And where is that? That capacitance is between base and emitter, because the charge that we deliver to this base region has to come from the emitter, right? Emitter and base, it cannot come from the collector. So we connect that to the between base and emitter, and we just give it a name. We usually call it CB. Okay, so that's almost the complete model of the bipolar transistor. All right, well, there is one little capacitance that we also need, and that capacitance is connected between the collector and ground. Not between the collector and the emitter, but between the collector and ground. That appears only in bipolar transistors that are integrated on a wafer, in an integrated circuit. So we call this CJC. Not CJC, we call it CCB or CCS. CCB. So CCB means collector bulk capacitance. Okay? And that arises because if I look at the structure of a bipolar device, when it's built on a wafer in an integrated circuit, we have the emitter up here with a contact. We have the base right under it with a contact. And then we have the collector right under it with a contact. all of these have to be contacted from the top of the wafer, right? We cannot contact from the bottom of the wafer. And then the wafer is all of this, which in this case would be n plus Pn. So this is P. And you can see that there's a junction between this and this. This is the wafer, we call it the substrate. So there's a capacitance between the collector and the substrate because we have a junction. You see, it's a reverse bias junction. So that's CCB, collector bulk capacitance or collector substrate capacitance. Substrate is also known as the bulk. Okay, so this now gives us the complete model of the bipolar transistor. And using this model, we can go ahead and analyze various circuits. So I just wanted to also mention that we have a name for this. We usually call this C mu. For historical reasons, we call this C mu. And this whole thing we call C pi. Okay, so sometimes I even draw this, these capacitances around the bipolar transistor symbol rather than draw out the whole small signal model, meaning that I draw it like this. I say, here's my transistor. I have a cap here, I call C pi. I have a cap here, I call C mu. And I have a cap here, I call to ground, I call C, CB or C, CS, and so on. Okay, so that's a good picture to remember for analyzing circuits at high frequencies. Okay, with 3 capacitors. So every bipolar transistor comes with 3 capacitors. And when we are analyzing circuits, we have to drop in these capacitors and then see what happens. All right, so next time we'll look at some circuits using this model just qualitatively, just to gradually begin to understand what limitations arise from these capacitors. I will see you